do ask lots of questions. Okay, so how are we going to reconcile this? Well, there's sort of two different options that you could envisage. You could imagine that it's the particles that are fundamental. So maybe it's the photons that are the fundamental object. And if you pack enough of them together, then that's what gives rise to what we call the classical electric and magnetic fields. Okay, that's one possibility. The other possibility that you could imagine is that it's actually the field that's fundamental, and that when you quantize the ripples of a field, that's what gives rise to particles. Okay. Now, it turns out that sort of both of these viewpoints have some validity, but it's certainly fair to say it's the latter viewpoint which has been the most useful. So this idea that it's not the particles that are fundamental. What's fundamental are fields, and that there are little ripples of these fields, and when you quantize those ripples, that's what we call particles. So for the electromagnetic field, that's what we call a photon. But now we're in a situation where we have to start introducing new fields for all the other particles that we know of in the universe. So we should introduce an electron field, and a quark field, and a W boson field, and a gluon field, and a neutrino field, and so on and so on. Okay? So that's sort of the basic premise of quantum fields. Okay. Good. So let me start by just sort of telling you why this is the right way of thinking. So why quantum field theory? Okay, so there's a bunch of different answers to this. Firstly, there's a zeroth order answer, which is for the same reason that people introduced fields in classical physics. And that's because of locality. You know, the reason that Faraday and Maxwell and Einstein were thinking in terms of fields was so that if something happens here, an electron moves, we're not thinking that it physically influences something over here immediately. What happens is it influences a field in its vicinity. That field influences nearby fields. Everything ripples and ripples, and finally it influences something here. And there was never anything non-local happening. Okay, so that's true in classical physics, and it's also true in quantum field theory. But there's a couple of much deeper, more profound reasons to do with the Q in quantum field theory that also holds. So let me just try and explain what they are. Okay, so there's a couple of answers I want to give. So answer one is because all particles of the same type are indistinguishable. Okay, so you presumably know about this already from courses in quantum mechanics. It's the statement that if you have two electrons in front of you and you swap them around, then the state of the universe hasn't changed at all. Okay, it's changed up to a minus sign, but that minus sign isn't important for this current discussion. And you know, you've probably not even thought just how extraordinarily amazing this fact is, that all electrons are exactly the same as all other electrons. All protons are exactly the same as all other protons. It's sort of mind-boggling, but to put it in some perspective, you could get a proton which was created in a supernova, which you knew happened 5 billion years ago in some galaxy far, far away, and you could compare it to a proton that you freshly minted in a particle accelerator here on Earth, and they would be exactly the same. And not just exactly the same like you know, the two red pool balls on the table outside are exactly the same, but you know, exactly the same in an indistinguishable sense where if you swap them around, nothing changes. Okay, that's pretty amazing. Why aren't there sort of errors in the production process? How can something created all that time ago, or you know, so far away, be exactly the same as something that was created here on Earth? So there's some words that you can drape around this, and the words are the following: that there's a fluid, a sea of stuff, sort of proton stuff, that fills the entire universe, and when we create a proton particle, what we're doing is we're taking a ball of this, and we're molding it using quantum mechanics into a particle, and then it looks exactly the same as something over here, because they're both made of exactly the same underlying stuff. Okay, so that's really the basic idea underlying quantum field. There's actually a bit more to this story, which is to do with that minus sign. You know, you take two particles, two electrons, you swap them around. It's not exactly the same state, right? There's a minus sign in the wave function, which comes from Fermi-Dirac statistics and gives rise to the Pauli exclusion principle, which gives rise to all of chemistry and all of biology and all of life as we know it. It's that quite important minus sign. Now, in quantum mechanics, when you learn about statistics and its relationship to spin, it's really something which you're just told. You're told spin half particles should be fermions, spin zero particles or spin one particles should be bosons, and they don't pick up a minus sign. It's sort of an extra thing that you have to put on top of quantum mechanics. One of the things we'll learn in this course is why that is true, why this relationship between spin and statistics has to be true. And this will come out of quantum theory. Okay, are there any questions about this? Okay, let me tell you answer 2. Answer 2. And it's because special relativity plus quantum mechanics implies that the number of particles you have in your system isn't conserved. By the way, how are these blackboards? If I write at the bottom here, can people in the back see? What's a good cutoff? That line's a good cutoff? Okay. So this says because special relativity and quantum mechanics implies that particle number is not conserved. From now on, I'll try and write above that line. Okay, what does this mean? I'll give you some examples about how this appears at the moment. Actually, I can tell you immediately. Google a picture from the RIC particle accelerator in Brookhaven, or better still, the star detector in RIC. What you'll see is this incredible explosion of particles flying out. There's about 10,000 particles that fly out of a typical collision at the RIC accelerator. These are created by firing together two gold nuclei, each of which has of order 200 nucleons sitting inside it. So it's a dramatic example of how particle number is certainly not conserved when quantum mechanics and special relativity, in this case high energies, combine together. What this means theoretically is that if you try to take the Schrödinger equation, which typically describes a single particle, and you try to generalize that to a relativistic version of the Schrödinger equation, which still describes a single particle, you ain't going to make any progress. Something's going to go wrong. Now, I just learned that on Thursday and Friday, Malcolm Perry told you how to take the Schrödinger equation and generalize it to relativistic examples of the Schrödinger equation, the Dirac equation, the Klein-Gordon equation. If you were to treat those as single particle equations, that is, the psi that appears there, you were to think of as the wave function for a single particle, you won't make any sense of that equation. Okay, I think Malcolm just sort of skirted around some of these issues. But you'll see that things go horribly wrong. You have to make sense of negative probabilities. No one knows how to do that. You'll find that you have infinite towers of energies which are unbounded below, and it's not quite clear what to do with that, although you can sort of just about get around it. You'll find that even though you think, because it's relativistic, the equation is causal, you'll find effects propagating faster than the speed of light. And what's happening is that in trying to write down this single particle relativistic wave equation, you've missed all the key physics, and this is the key physics. It's that there is no relativistic system with a fixed number of particles. Typically there'll be swarms of particle-antiparticle pairs around this fixed, this single particle you started with. So let me just write down something quantitative about this. Okay, so consider a particle trapped in a box size L And we know that Heisenberg tells us that we don't know the momentum of that particle. There's some uncertainty, and the uncertainty is of order h bar over L. But if we're in a relativistic context, then one guy's momentum is another guy's energy. These are things which just transform into each other under Lorentz transformations. So somebody in a different frame is going to see some uncertainty in the energy of the system. So plus relativity is going to tell us that there's an uncertainty in the energy which is of order h bar times c over L. But when the uncertainty of in the energy is getting so large that it's comparable to the mass of the particle you started with, then there's enough uncertainty for you to start creating particle-antiparticle pairs out of the vacuum. And I put the two there because typically you do need to create these things in pairs. Okay. Okay, the upshot of this is if you try to localize a particle in a small enough box, where I've dropped this 2 because this is all sort of order of magnitude estimates. But if you try to localize the particle in a box which is smaller than h bar over the mass of the particle times c, then it's not even possible to say that there's a single particle anymore. Because within that small region, there's a very likely chance that if you try to detect the particle, you may instead detect one of the particle-antiparticles, which has just popped out of existence from the vacuum around it. So the length scale that appears here is called the Compton wavelength. And the way to think about this is that it's basically the maximum length scale at which it makes sense to talk about a particle at all. Because if you start exploring the particles at length scales smaller than this, what you're going to see instead is a swarm of particle-antiparticle pairs that surround the particle. Okay? Remember, there's another length scale associated to quantum mechanics of particles, and that's the de Broglie wavelength. This is much, much smaller than the de Broglie wavelength. Right? That's h over p, the non-relativistic momentum. So a good way to think about it is that the de Broglie wavelength is where the particle first starts to exhibit wave-like properties, and the Compton wavelength is where the particle sort of ceases to make sense as a particle at all. It's really, in some sense, the size of